Last night was about maximums and minimums, and increasing and decreasing intervals. And today we're going to talk about something called concavity. Now the concavity of a graph is whether or not a graph curves upward or curves downward. And on page 299 you can look at some pictures where they're showing you things that are concave up and concave down. So you might want to look at that at home. I'm just going to draw some curves. So this curve would be said to be concave down. See, it's curving down. That would be concave down. This is concave up. And right here, where it switches from concave down to concave up, this is called the point of inflection, the POI, the point of inflection. The point of inflection is the point where the concavity is going to switch on these curves. So if the first derivative is increasing, then the original will be concave up. Let's think about that. If the first derivative is increasing, then the original will be concave up. What is that saying? That's saying, let's suppose we have, here, this will be my original. So my original is going to be an x cubed function. So here's f. And from that, my derivative measures the slope. So these slopes are positive. So my derivative will be positive until right about here. These slopes are negative until right about here. So my derivative will be negative. And then these slopes are positive again. Okay, so here's f prime. It says, so somewhere right around in here, the first derivative switched. Okay? So it says, if f prime is increasing, so here's f prime, the green graph. If f prime is increasing, which would be this piece, then the original will be concave up. Well, look at the blue graph, right about where this point is, right about here. What does this curve do? Curves up, it's concave up. So when the first derivative is increasing, the original is concave up. Well, what are we talking about the first derivative when we're talking about it increasing? We're talking about the first derivative slope. Well, what would measure the first derivative slope? That's right, the derivative of the derivative, the second derivative. So if the first derivative is increasing, then that means its slope is positive, and the slope of the slope would be the second derivative. So the second derivative is positive when the first derivative is increasing. Well, when the second derivative is positive, the original will be concave up. When the first derivative is decreasing, so see my green curve, my first derivative is decreasing, look at the original. It's concave down. Well, what measures the decreasing of the first derivative? The slope of the slope would be the second derivative. So when the second derivative is negative, the first derivative is decreasing, which means the original will be concave down. So the second derivative is going to be used to analyze concavity on the original. The second derivative measures the slope of the first derivative. It measures the concavity of the original. So the concavity of the original is related to the slope of the first derivative. So the way we test concavity, it says if the second derivative is positive, then the original will be concave up, because that means the first derivative would be increasing. If the second derivative is negative, then the graph of the original will be concave down, because that means the first derivative is decreasing. And if the second derivative equals 0, then the original will be linear. There will be no curvature. There will be no concavity. It will just be a flat line with no concavity. So let's look at these three graphs so you see that relationship between the original, the first derivative, and the second derivative. So here's my original graph. Ben's favorite ballerina. Ben, this lesson is for you. So we've got Ben's x cubed ballerina. And let's notice notice some things about the ballerina, the x cubed graph. What's it doing in terms of slope the whole time? It's increasing. So positive slope, positive slope. There's my first derivative. The first derivative of x cubed is 3x squared, which makes this parabola. Well, let's notice some things about the parabola. This is increasing, so the slope values are positive. What are the values? The values of this parabola right here. When x is -2, the y value is positive. When x is -1, the y value is positive. When x is -3, the y value is positive. These are all positive values because these are positive slope values. It's increasing. Then it continues to increase. It continues to increase, which means the values continue to be positive derivative values. Now, what is the second derivative measure? Well, the second derivative is of 3x squared is 6x. The second derivative measures the slope of the first derivative. This is decreasing, so the second derivative values are negative. This is increasing, so the second derivative values are positive. Come over one more, the second derivative analyzes concavity of the original. Concave down, first derivative decreases, second derivative has negative values. Concave up, first derivative increases, second derivative has positive values. So when the second derivative has positive values, you know the original curves up. When the second derivative has negative values, you know it's concave down. So how do we figure out concavity? We're going to need to know the second derivative values to figure out concavity. So determine the intervals on which f of x equals 6 times x squared plus 3 to the -1 power is concave up or down. So step 1 says we need to locate the critical numbers for the second derivative. When we're talking about concavity, second derivative should pop in your brain. When we're talking about slope, first derivative should pop in your brain. So we need to get the second derivative. Well, before we can get the second derivative, we need the first derivative. So let's get the first derivative. And what rule is happening here? Chain rule. So we get -6 times x squared plus 3 to the -2 power. Go to the inside, derivative of x squared is 2x. So if we clean that up a little, we get -12x over x squared plus 3 squared. So now we need the second derivative. What rule do I need to use to get a second derivative? Well, I could use the quotient rule, or I could have left it like this with the negative exponent and use the product rule. You can use whichever rule you're more comfortable with. I'm going to use the product rule only because I happen to use the product rule on this key when I made it, but it really doesn't matter which. Product rule or quotient rule comes out to be, if -12x hangs out, we do the chain rule, we get -2 times x squared plus 3 to the -3 times 2x plus x squared plus 3 to the -2 hangs out, and the derivative of -12x is -12. I pulled out GCF. No, I didn't pull out a GCF. Actually, I moved these to the bottom and simplified. So -12 times -2 is 24, times 2 is 48, x squared over x squared plus 3 cubed. Over here, the -12 stays on top, over x squared plus 3 squared. What would the common denominator be? That's right, the common denominator would be x squared plus 3 cubed. Nothing happens to the first fraction. What do I multiply the second denominator by? X squared plus 3, so -12 times x squared plus 3 is -12x squared minus 36. So we end up with 36x squared minus 36 over the denominator. Okay, so that's my second derivative. And we need to find these critical numbers. Well, where do you think critical numbers occur for a second derivative? They occur where the second derivative equals 0 or is undefined. So I need more space, so I'm going to erase. Hopefully you can pause the video if you need to and copy all that work down. But the second derivative, let me just write it right here again, was 36x squared minus 36 over x squared plus 3 cubed. Okay, so we need to find critical numbers. So we got to find where the numerator equals 0. We also need to find where the denominator equals 0. Let's start with that denominator. Is there anything that I can plug in for x and square it and add it to 3 to make that equal 0? I put in a positive number, it's going to be positive. I put in 0, it's going to be positive. I put in a negative, I square it, it becomes a positive plus a positive. Will this ever make 0? No, so there's nothing that makes the denominator 0. On the bottom, we get x squared equals 1, so x equals plus or minus 1 are my critical numbers for my second derivative. Step B, do a sign test for the second derivative. So I'm going to label this sign test the second derivative, because you're going to have problems where you will do both the first sign test and the second derivative sign test. If you don't label them, you'll get them mixed up. Pick an easy number to test. Pick 0. We're going to test the second derivative sign, which means we're going to plug the 0 into our second derivative. If we plug 0 into the second derivative, we get 0 minus 36 is negative. What's the bottom going to be no matter what I plug in? Positive, so when I plug 0 in, I get a negative over a positive makes a negative. None of these are double roots, so they alternate. So we want to figure out, where is it concave up? Well, it's concave up if the second derivative is positive. So if f is concave up from negative infinity to negative 1 parentheses, 1 to positive infinity parentheses. Now, unlike increasing and decreasing where we use brackets, with concavity intervals, it's going to always be parentheses. And then, where will the original be concave down? It'll be concave down where the second derivative is negative, so negative 1 to 1 with parentheses. So let's move on. That means on the original graph is curving down, then it's curving up, then it's curving down again. Of course, I don't know if this thing is increasing or decreasing because we don't know anything else about it, but we do know it curves up, then it curves down, then it curves up again. So let's go on to the next page. Now, what is a point of inflection? A point of inflection is a point on the original curve. As long as the original curve, F, the original curve is continuous there. So this is, you can only have a point of inflection where it's continuous. It's a point where either the second derivative at that point is 0 or the second derivative is undefined. So first, it's a critical number for the second derivative. And, big and, the concavity must switch from upward to downward or vice versa. So the second derivative sign test must switch. This is crucial. There is a very popular multiple choice question they like to put every year that says, find your points of inflection. And every student knows, oh, to get my point of inflection, I find my critical numbers for my second derivative. And they find where the second derivative equals 0. And let's say they found where the second derivative equals 0 and the x values came out to be negative 1, 0, and 2. And that's one of the choices. A, B, C, and D, and E. Letter B, there it is. Oh, I'm done. I've got my points of inflection. They go on. What they forgot to check was the sign test. Because when you do the sign test on this problem, they do every year almost, around one of those points, look what the sign does. 2 doesn't switch signs. So 2 is not a point of inflection. Because to be a point of inflection, and let me make sure you can see that too. Yes, good. To be a point of inflection, the second derivative has to change signs because the concavity has to switch from the original. So the only points of inflection are -1 and 0. 2 is not. So letter D is this choice. But everybody who didn't do the sign test already got it wrong because they went with the first half of the problem. You have to actually check that the second derivative changes sign so you know whether or not the original switches concavity. So to be a point of inflection, it has to be where the second derivative equals 0 or undefined, and you verify that the second derivative switches sign so you know the original switches concavity. So let's look at example 2. Determine the points of inflection of x to the 4th minus 4x cubed and discuss concavity. So the first thing we need to do is find the second derivative where it equals 0 and is undefined. So we need the second derivative. So first derivative is 4x cubed minus 12x squared. Second derivative is 12x squared minus 24x. Then we need to find where this equals 0 or is undefined. Pull out your 12x, you get x minus 2. So x equals 0 and x equals 2. These are potential points of inflection. We don't know for sure if they're points of inflection until we do what? Check to see if the second derivative changes signs so you know concavity switches. Let's check. So let's put 0 and 2 on the number line. What's an easy point to test? 1. We're checking the second derivative. Don't plug it into the first derivative. Don't plug it into the original. We're checking the second derivative sign test. So I'm going to plug it into this factored second derivative. So 12 times 1 is 12. 1 minus 2 is -1. What's a positive times a negative? It is negative. Are either one of these double roots? No. So they will switch signs, but you can always check. Plug 3 in, you get a positive times a positive. Plug -1 in, you get a negative times a negative, which is positive. The concavity does indeed switch because I went from positive to negative to positive. So on the original, F is concave up from -infinity to 0 and from 2 to positive infinity. And F is concave down from 0 to 2. What is my point of inflection? Well, I have one point of inflection when x is 0, the other when x is 2. How do I find the y coordinate that goes along with those x coordinates? Plug it into the original. Anytime you need a y coordinate, you plug it into the original. So if we plug 0 back up into the original, we get 0. So 0, 0 is a point of inflection. We plug 2 back into the original. 2 to the 4th is 16. 4 times 2 cubed, so 4 times 8 is 32. So 2 negative 16 is my other point of inflection. If they ask for a justification, how do we know those are points of inflection? Because F double prime switches